All right, welcome back. So today we are going to take on the second part of 8.2, which talks about the factors affecting solubility and the rate of dissolving. So what are we talking about today? Well, we're going to start with talking about like dissolves like, then we're going to talk about factors affecting solubility, and then factors affecting the rate of dissolving. So our learning goals for today's class are to explain the theory of like dissolves like, to list and describe the effect of temperature on solubility, to list and describe the effect of pressure on solubility, and to identify the factors that affect the rate of dissolving. So let's get started. Like dissolves like. Sounds pretty straightforward if we know what we're talking about. So, in terms of solutions, like dissolves like means that a solute will probably dissolve in a solvent if the solute and the solvent have the same polar or nonpolar nature. So if we took out the word like and threw the word polar in there, it would say polar dissolves polar. So we could do the same thing with nonpolar. Nonpolar dissolves nonpolar, which basically is what this chart sums up. So if we have a polar solute and a polar solvent, that solute is usually soluble. But if we have a nonpolar solute and a polar solvent, usually insoluble, not like. Same thing works with nonpolar. If I have this polar solute in a nonpolar solvent, it's going to be insoluble, but then we come back to like dissolves like, and that nonpolar solute is going to be soluble in a nonpolar solvent. So we know chemistry is not always straightforward. It's never as easy as we want it to be. So what happens when we have a molecule that has both polar and nonpolar components? Well, these molecules can dissolve in both polar and nonpolar solvents. A great example of this is soap and detergent molecules. So these are great because they can dissolve in polar solvents and nonpolar solvents. So if we think about oil, we made a salad, we have vegetable oil. If these detergents, if soap or detergent was only polar, there's no way it would dissolve in that nonpolar oil, and then our salad bowl will never get cleaned, right? But if it was only nonpolar and didn't dissolve in water, we would never be able to get rid of it. So that is what's so amazing about soap. Both components, polar and nonpolar, it's soluble in both types of solvents. And as we can see, we have our soap molecule here. So here's our hydrophobic region, which is the region that does not like water, and our hydrophilic region, which is the region that does like water. And these two regions come together, and that's what makes it possible to dissolve soap or detergent into both polar and nonpolar solvents. All right, so now we're going to talk about temperature and solubility. So, the solubility of many substances change with temperature. For a given solid solute and a liquid solvent, so that's when we would be putting a solid into a liquid to create a solution, solubility usually increases with temperature. And we can show this using a graph. So a graph that shows the relationship between the solubility of a solute and the temperature of a solvent is called a solubility curve. So here's an example. So if we look over here, we have temperature across the x-axis, grams of solute per 100 grams of water on our y-axis, and then different colors representing different compounds to be dissolved, in this case in water. So we can ask a bunch of questions and answer a bunch of questions using a solubility curve. If we were to do an example, we would say, the question I have here is, according to the graph, what is the solubility of potassium nitrate at 30 degrees Celsius? So I go, okay, I come to my graph, I look, all the different colors, where is potassium nitrate? Ah, here it is. So I go, okay, they want to know 30 degrees Celsius. So I find 30 degrees along the x-axis, trace the line up, and I see that 50 grams of potassium nitrate is soluble in 100 grams of water. And I could do that for any of the given compounds on this solubility curve. And yep, I was correct, and I'm so sure that you were as well. 50 grams are soluble in 100 grams of water. So we talked about a solid into a liquid. Now let's talk about the solubility of a liquid into another liquid. This is usually not affected by temperature. And the same goes for gas. So a gas into another gas, the solubility is not affected by temperature. But what if we have a gas into a liquid? Well, That depends on both temperature and pressure. But we're going to focus in just on the temperature piece, and we'll see that usually the solubility of most gases in most liquid solvents decrease with an increase in temperature. Okay, so if we're always thinking about increasing temperature, if I'm taking a gas solute, putting it into a liquid solvent, as I increase the temperature, the solubility of that solution is actually going to decrease. Okay, whereas when we had our solid solute into our liquid solvent, we increased the temperature and the solubility actually increased with temperature. Okay? Now we're going to turn the tables a little bit and focus more on the environment and increased temperature specifically. So all important gases in the atmosphere like oxygen and nitrogen actually become less soluble in water as the temperature of water increases, which makes sense because that's what we just talked about in our last slide. So this turns into an issue when we talk about heat pollution and the warming of the earth. There can actually be very serious consequences. Okay? So the main problem is that the transfer of waste heat, which is that heat pollution, to a body of water lowers the concentration of oxygen, right? Because we said when a gas is dissolved into a liquid, we are going to decrease solubility as temperature increases. So our water is getting hot. The concentration of oxygen dissolved in the water is now lower because the temperature has gotten hotter. And this affects the organisms that live in the water. They become more susceptible to disease or they die from oxygen shortage. Okay, so we might not think, oh, we don't live in the water, it's not a big deal. We can breathe, we have oxygen in the atmosphere. We need to think about the organisms around us and see that this is a problem for them as well. All right, next we're going to talk about pressure and solubility. So we just talked about temperature, we're going to move on to pressure. So pressure has very little effect on the solubility of a liquid or solid, but it has a significant effect on the solubility of a gas. So the solubility of a gas into a liquid is directly proportional to the pressure of that particular gas above the liquid, but not any other gases. Whoa, let's break that down. So let's think about carbon dioxide, okay? So I have a beaker sitting in front of me with water, and I have some carbon dioxide in my water. The pressure of the carbon dioxide inside the water part of the beaker is directly proportional or the same as the pressure of carbon dioxide outside of the water in the beaker. Doesn't matter about the pressure of oxygen, doesn't matter about the pressure of nitrogen, they're specific to each other. Okay, so a real life example of this, because when do we use chemistry in real life is always the question. Here's my answer for you. A soft drink, a pop, a Coke, a Sprite, whatever you like to drink. A soft drink is bottled with a high pressure of CO2 to increase the solubility of the gas in that drink. So we have our closed bottle, we twist it open and we can hear it, right? It all kind of fizzes, doesn't explode unless you shake it, but it fizzes out a little bit. And that's because the pressure is lower outside of the bottle. So it's going to raise up and come out. All right, so now the last thing we're going to talk about today is the factors that affect the rate of dissolving. So the rate of dissolving is just a measure of how quickly a solute dissolves into a solvent. So rate and speed. So how fast does a solute dissolve into a solvent? So there are three main factors. The first one is agitation or mixing. So what this does is it just increases the number of collisions between solute and solvent particles, right? So I love tea. I love to drink tea. So I have my tea and I put my little bit of milk in it, but then I also put some sugar. And if I just sit there and just waited and decided I would just wait till the sugar mixed on its own to drink my tea, it would work, but it would be cold and I probably wouldn't be thirsty anymore. So what I do is I put my spoon in and I stir it or I mix it to make the sugar dissolve faster into the tea. Okay, our second factor is temperature. So what the temperature does is it increases the kinetic energy. So kinetic is movement, right? So all of these molecules are moving around, these compounds are moving around, and at higher temperatures, their kinetic energy is increased so they can run into each other more frequently and they can dissolve faster. And lastly, our third factor that affects the rate of dissolving is surface area. So the larger the surface area, the more collisions with the solvent molecules, which makes the solute dissolve faster. Okay, so again, that's three factors that affect the rate of dissolving: mixing or agitation, temperature, and surface area. And the rate of dissolving talks about how quickly that solute is going to dissolve into that solvent. And that's all for today's lesson. I hope you enjoyed it. Thanks for watching.